So Monday is 10 a.m., Wednesday is 11. All right, so it's the same as the usual class time. While we're at it, the 2:15 final is at 12, not at 12:30, even though the class is at 12:30. The exam is 12 o'clock to 2, so if you come at 2:30, you're missing a half hour. Sorry, you had something else?
They're going to be 2 hours long?
2 hours, yeah, hour 50 minutes. So let me talk briefly about PA5 first, and then we'll just make a few comments on the final. So PA5, that's graded, and I gave some feedback and so on and so forth. Let me make a few comments. So if you know if your program works or not, right? Because there was sample code out there, so you could run some test cases and compare. If your code was not giving the correct number of trials, in the cases that I tracked down, it was usually just a problem with this function, right? With implementing this algorithm. So it might be that somebody used f instead of f minus 1. Or in some cases, people switch the order of these arguments partway through the function. So it might have been floors and eggs, and then down here they were passing eggs and floors, right, or something like that. So little things like that will drastically change the result. In some cases, people were iterating from floors 0 to floors minus 1, or from 0 to floors, or from 2 to floors, or things like that. Right. The way this is written, our floors go from 1 up to floors, and so you iterate f between 1 and floors inclusive. Find 2 recursive calls to egg, right, with those arguments. Take the largest of those, add 1, and then find the smallest of that expression over all the values of f. And a lot of people wrote max-min functions, which is fine, but here's something that I saw in a few cases. All right, if A is less than B, return A. If B is less than A, return B. So what's the one problem with that? If they're equal, you're not saying what you should return. And if you don't specify return, well, the calling program is still going to look where it expects a return value to be, and it's going to give you that as the return value. And sometimes you'll luck out, it'll be A or B, but sometimes it'll be something totally random, right? And so that was happening in some cases, and it may let this work in some edge cases, and then in some other cases it gives you weird values. So things like that, but basically, finding the largest of these two, adding 1, finding the minimum over those floors. In cases where your code was seg faulting, there were 2 main things. One was mixing up eggs and floors, but the bigger issue was still a problem somewhere in this expression, where, for example, if you switch around eggs and floors right as possible, you might call this with a negative value of eggs, right? And if eggs is negative, there's no base case for that because it should never be negative, but if you try to look up a negative eggs index in your save array, you'll probably seg fault, right? Or if something's going totally out of sorts in here and your floor is getting to some huge value like 10 million, right, and you try to access that in your save array, you'll seg fault. So if you weren't getting the right answer, or if you were seg faulting, it was probably a pretty small issue in that expression, right? Either you're finding this expression or iterating over the floors. Okay, so tomorrow's an open lab, so if you want to work on your code during class time, right, come in. I'll be here both periods. We can look at what you were doing and dig into it. The other thing I want to discuss, though, is how you add dynamic programming to this or to other algorithms in general, because I saw a number of different ways of doing this, and I want to make sure you got the essence of of the way we were talking about. So here's a general program. So here's your slow recursive function, okay? So knapsack, rod cutting, longest common subsequence, egg dropping, all of these problems are recursive, and they share this fact that when you try to solve this problem for some particular argument or set of arguments, you end up solving the problem for a lot of other sets of arguments, okay? And the recursion can get really, really wide. You might end up calling the same, passing the same arguments to your function again and again and again, okay? So typically our function will be, you know, some thing called slow. It takes some arguments, which could be more than one. It returns whatever. I'm just going to say an integer. And this is really slow stuff. And you're making all kinds of calls to the slow function, okay? And you do more stuff, and you're doing stuff in here. And eventually, you know, somewhere, you come up with an answer, and you return that answer. Okay, that's basically what all these things look like. So here's the thing. If you want to add dynamic programming this, if you want to speed it up by eliminating repeated recursive calls to cases you've already solved, don't change any of this. Okay, all of this should stay exactly the same. And some of the PA5s I saw started taking this and changing it with, you know, if save is not equal to 0, then do save bracket f minus 1, bracket eggs minus 1, etc., etc. Don't monkey with that stuff, okay? Write this code and it should work for small values where you're not doing too much recursion. Once this code is working, leave it alone, okay? To add dynamic programming to this, you only got to add 3 things. You're going to add something right before your return. You're going to add something right before you start. And you're going to add something outside. Okay, so what do we add outside? Well, this is where we use a global variable to save the values of this function once we calculate them. So if these are integers, it's going to be integer save bracket, and there could be, you know, multiple dimensions and so on. But some sort of structure in memory that you can use to save values of your function. And generally we want to initialize it. If we know that 0 is never going to be a function result, we can initialize it to 0 by just saying equals bracket 0. If 0 could be a function result, we can load some other value in there, or we could make a structure with a flag saying have we saved it. But the essence is the same, right? We just want a big array where we can save return values, and we want to initialize it to something so we know if there's anything saved in there or not. And then in the beginning of your function, see if you've already calculated this. If save bracket args is not equal to 0, just return it. So in this case, save args is not 0, just return save bracket args. If you haven't already calculated this function for that particular set of arguments, though, this will fail because it will be 0, so you'll go ahead and do all the slow, expensive, time-consuming stuff. You'll come up with your answer. Now, before you return, just save that. Save bracket args equals answer. And that's it, right? It's just 3 things, and it's always going to look like this. So before you start any of the work in your function, see if you've already saved a value for these arguments. If you have, just return it. If you actually go through and do all the work to calculate an answer, save it before you return, and then make a global array outside to save all of these results in memory. Does that make sense? All right, that's all there is to dynamic programming. It's really just a memory cache. All right, so any questions before we just kind of run through what's in this study guide? So things you should be prepared to do on the exam. Definitely writing code. Okay, there's 10 questions on the exam. There's 3 programming questions worth 15 points each. So 3 questions, about half your points. And then there's 7 questions that are manipulating trees, answering questions about data structures, doing sorts, stuff like that, short answer, and so on. So about half the points are programming, but it's only 3 questions. All right, so write code to work with structures, manipulate structures, and so on and so forth. I may ask you to write a function. I may ask you to write a few lines of code. I may ask you to write a whole program. Okay? Try to be really sure that what you're doing is what you're asked to do and nothing more. And if you're in doubt, ask. Right? And I'll try to clarify during the test. So structures, pointers, dereferencing pointers, malloc and free, all the stuff we've been doing, defining structures, accessing fields in a structure, and so on and so forth. So analyzing code that I give you. So here's a set of code, make some changes to it or answer some questions about what it does. Definitely recursive code. Okay, so go back and look at the recursive code we've been doing. Tree traversal, tree search, tree insert, and so on. And think about it in terms of the recursion, right? Not just in terms of lines of code that make it work, but what's going on recursively, right? Why can I find the height of a tree by using the height function, right? Because it's 1 plus the height of the tallest subtree. So think about that, right? Because I'll ask you to do some recursion on the test. List trees, tries, hashes, we'll talk about those up top. GDB, so you should have a fairly familiar relationship with GDB at this point. Okay, so compile with the -G switch. To run GDB on a program, you say GDB space name of the executable. Inside GDB, if you want to set up command line arguments, set arg blah, right? And then start to begin execution of your program. And then you can say continue to say just free run. You can say set break to set up a breakpoint. You can say set watch to set up a watch point. You can print the values of variables with print. You can list your source code with list. You can examine memory with X. Step and next. Okay, next goes to the next line of code. Step goes to the next thing, including stepping into a function call. So just those kinds of things, right? If you're rusty on it, just write some code and play around with it for 5-10 minutes. Do some steps, do some next, get into trouble, get out of trouble, and just be comfortable with that. Val grind, right, is for dealing with memory leaks. So mostly it's just val grind, and you type your program name as usual, and you run it as usual, and when your program exits, you get a report, right, which tells you if you have memory leaks. But val grind also watches for uninitialized memory and gives you messages along the way. Make files, I'd like you to be able to construct a basic make file. It doesn't have to be terribly fancy, but at least to this degree of fanciness, which is, you know, here's our main program, which needs some .o files, and then how about that? So main is a main program we're building. It depends on some .o files, and so to build it, we just say gcc-o, name of the output file, right, the program we're creating, and then the .o files that we use to build it. And then for these .o files, you know, file 1.o depends on file 1.c, and use the -c switch. Right, so I want you to know how to use the -c switch and do it effectively, as opposed to just main depends on everything .c and just compile all the .c files, because that recompiles everything anytime something changes. So this just gets you a little more nuanced. and maybe your file includes a .h, so list that as a dependency. So if that .h file changes, it'll say, oh, I have to recompile f2.c. But you don't compile include .h, right? That doesn't go on the GCC line. It gets compiled because it's included in this .c file. So don't include the .h's. Other than that, everybody seems to know how to do makefiles anyway, so not a whole lot to worry about there. Sorts, we'll talk about up top. So I'll do this from the bottom up for time efficiency because the earlier stuff we've already seen on the midterm and talked about. So heaps, max heaps and min heaps, okay? These are identical in how you work with them except for what we call the heap property. In a max heap, the heap property is that the root should be larger than the value of its children. In a min heap, the root should be smaller than the value of its children. Everything else is the same. Up heaping, down heaping, it's all the same procedure. So the main operations on a heap, to put something into a heap, you add it to the last position on the heap, okay, deepest level, the next open spot, and then you upheap. Okay, you work your way up and make sure the heap property is satisfied. To delete from the heap, you remove the root, replace it with the thing from the last position in the heap, and then you down heap. Okay, those are your two basic operations, insert and delete. Heapifying was this fancy way we talked about taking a set of data and building a heap out of it directly as opposed to inserting one number at a time. And we talked about implementing a heap with an array, so starting at index 1 and then just using pointer, using index arithmetic to find children and parents. So take a node's index, double it, and you get the child. And divide by 2, you get the parent.
So when we're working with like sorting structures in the final, is it going to be like through like code, or are we just going to have to demonstrate that we know? Like,
could be code, could be here's a list of numbers, show me the first 5 steps of an insertion sort, that kind of thing. All right, so sorts, bubble, insertion, selection. These are the order n squared sorts. They're the fairly inefficient ones, but fairly straightforward. Bubble, you've known for a long time. Insertion, you select things in sorted order. You insert things in sorted order. Selection, you select things from the input in sorted order. Merge sort is an n log n sort. It's recursive. Split your list in half. Sort both halves and then merge them together, interleave them in sorted order. And the way we sort the sublist is by using merge sort, so it's recursive. Heap sort is, put things in the heap, add it to the end and upheap and so on and so forth. Quicksort is another n log n, and that's the one where you have a series of numbers and you have a pivot on the end. And you have a pair of pointers, so you look for numbers on the left that are smaller than your pivot, and when you find something that's not, you stop, and then you go from the right looking at numbers that are bigger than your pivot, and when it's not, you stop, you swap them, and then you continue. And when you're done and both arrows have met, you swap that number with the pivot, and now your pivot's in the correct position. Okay, we spent a lot of time talking about this. We worked out a bunch of these on the board. We worked out some on the display. There's a good chance you're going to work one out on the exam. Okay, that's a hint. So make sure you know how to do the quick sort, showing it step by step, right, every time you swap things. Radix sort was where you sort digit by digit or letter by letter, and that's arguably order n, but the time can be really long. Dynamic programming, we just talked about, caching results. So if you have an algorithm that's heavily recursive, you can speed it up by saving results you've already calculated. Tries, so tries are the big wide structures where you have, say, a node containing 26 children and this end of string field. And I'd like you to understand the concept of a try. I'd like you to be able to look at a try and figure out some of the words that are stored in it, and I'd like you to be able to take a picture of a try and add words to it, okay? Or answer questions about what's in there. So we did this in class. I gave you a handout and we put put some words in and modified it and so on. So make sure you're comfortable with that, because that's good material for the exam. All right, ABL trees, these were the balanced trees. So they're binary search trees, but we try to keep them balanced. So we had this notion of a balance factor. Balance factor was the height of the left subtree minus the height of the right subtree. So every node has a balance factor. And it's basically the difference in the heights of the subtrees. And balance factor is not calculated using balance factor. It's not this factor minus that factor. It's based on height. Okay, so at each node you can find the height of the left subtree, subtract the height of the right, that's the balance factor. So you should be able to take a picture of a tree and figure out what the balance factor is at each node, which means you want to know that definition, you want to know how to calculate height. And then if you add a node to a tree and you recalculate the balance factors and you find a 2 or a minus 2, the tree is unbalanced. If everything is 1, 0, or minus 1, it's balanced. But as soon as you hit a 2 or a minus 2, there's an imbalance. And you can restore balance by doing 1 or 2 rotations. And the particular rotation or rotations you have to do comes from that table. Okay, so I never posted that on Canvas, did I? All right, I will post a link to that. So make sure those rotations are on your note sheet if you haven't memorized them. And basically 1 to 2 rotations will restore balance. So you should be able to take a picture of a tree and find if there's an imbalance, and if there is, describe the rotations to perform, right, left, right, 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 that kind of thing, and then actually make that correction and draw the balanced tree. Trees, we spent a lot of time talking about binary search trees. So main property, if you have a node, everything to the left is smaller, everything to the right is larger. Depth of a node, number of links from the root to that node, and height of a tree, which is the depth of the deepest node. Okay, height of a node, the tree containing just a root is going to be 0, because there's only one node and it has no distance from the root. Height of an empty tree, by definition, is -1. Balance we talked about, right? You can calculate balance factors, but there's also a recursive definition of balance, which is left and right subtrees are balanced, and left and right subtrees have a height within 1 of each other. Balance factor of no bigger than 1, less than -1. All right, we talked about 3 types of depth-first traversals: left node right, node left right node. Okay, they're recursive by their nature. The code for traversing in these can be recursive, and printing out the root node just comes in different spots. We talked about a breadth-first search, which is where we basically move across each level, and that's implemented using a queue. Recursive routines for manipulating trees, for searching, for inserting. Okay, those are all recursive in nature. Again, think about not just the code that lets you insert using recursion, but think about why that works. Logically, why does it make sense to say, if my number is smaller than the root, I can just say insert into the left subtree, right? So that's just kind of moving on that path towards being able to think of things recursively. And then deletion, right? You should know how to delete from a binary tree, and the algorithm we've used in class is replace the node so it only works for deleting roots. Replace the root with the largest node from the left subtree. Right, take it, move it up to the root, and then everything on the right will still be bigger. And the one exception was if there was nothing in the left subtree. If it didn't have a left subtree, then you can just move the root down to its right child. So you should be able to take a picture of a tree and delete a node from it and show what the resulting tree is. So review that algorithm, right, which is take the largest node, replace the root with that, and then if that node had left children, let that node's former parent adopt those children on its right, because it's lost its right child. All right, hashes. So here's an example of a hash. You want to look up somebody's phone number, right? And you could have a book with the names and phone numbers of every person that you know. We don't do this anymore, but we used to. You gotta have a book with the name and phone number of every person you know, right? You just flip through it page by page looking for your friend, right? We actually use a hash. So what do? We have a hash function which says, well, take the person's name, look at their last name, look at the first letter. And that first letter tells you where in that address book you should look for this person. And they're probably not alphabetized in there, right? But it's a small section. You only have 5 friends with the last name that starts with the letter H. So you've only got a few names to look for, okay? That's basically what we did in PA3. So we used a fancier hash function. Instead of just taking the first letter, we combined all the characters in the license plate and used that to figure out where we should look for this license plate. So a hash function in general takes a key, a thing you're looking for, turns it into an integer, which is a location in an array. And if you're using chaining, which is what we used in PA3, that location in the array gets you to a linked list. And now you just search the list and look for the license plate or whatever your key was. If we're not using chaining, we can use something called probing. And there the idea is hash the name, tells you it should be stored at this location in the array. If it's not there because something else is there, hash it again. Get a different hash number, check that location. Right, so probing is just hashing repeatedly and getting different locations. All right, stacks and queues. Stacks are last in, first out structures. Queues are first in, first out. We didn't spend a lot of time on these. We didn't write any code for them, but think about just sort of the high level concepts. Last in, first out versus first in, first out. Think about if you were to implement these using lists, what would that look like, right? Don't worry about this arrow, that equals this, well, this is not equal to null and so on, but higher level, right? Just think of a linked list as a thing that you can insert, you can remove, and so on. How would you use that to implement a stack? Well, you insert in the beginning, you remove from the beginning. How do you implement a queue? Well, you insert at one end, you remove from the other end, right? So those are good ways to think about stacks and queues, is how do you use them to do these things. And we can implement them using arrays. We didn't really do anything like that with code. So if I asked you something related to coding those, I would probably give you some code to work with. Recursion, pretty much everything we've been doing after list has been recursive. And most of what we do in 223 will be recursive or recursion based. So keep thinking about that. Abstract data types, right? This idea that there's this difference between how something is implemented versus how somebody uses it. So when we make a linked list, you can think of your main program, how does it interact with the list? Well, it says insert and find and print and so on. That's thinking of the list as an abstract data type. But is it implemented with an array? Is it implemented with pointers? Is it implemented as a binary tree, right? Those are the implementation details. That's different from the abstract view of a list, right? So all of our structures, we can think of them abstractly. That's basically a view from whoever is using them, as opposed to the view from whoever is actually writing the code to implement them. So that's all an abstract data type is. We talked about makefiles, GDB, malloc free, valgrind, pass by value versus reference. There's not much to worry about there. Everything is passed by reference, or passed by value in C. Stars and ampersands and dots and arrows, right? That's just pointers, dereferencing pointers, pulling fields off of structures and so on and so forth. And linked lists, structures, allocating memory, that's all stuff that, you know, we talked about. You studied that for the midterm. Nothing new really to say there. So I don't expect the final exam to be like horrifying. It might take you a good chunk of the hour and 50 minutes, but I think everybody here knows how to do everything that's on the final. So it's harder in a timed situation, and if you're studying for other exams and so on. But modulo all of those details, right, I don't think it's going to be a horrible experience. And I think everybody in here is in really good shape. I think you've done a fantastic job learning some data structures and thinking about programming and manipulating memory in a very different way from, say, 224 or 121. And I think that change in being able to think about the stuff is the essential lesson from this course, and it's going to work well for you in 223 and then wherever you go beyond Clark. So I think everyone's in good shape, and I'm excited for spring quarter, even if it is online. I think it'll be a good experience. So any other questions, comments, concerns? I'll be here tomorrow. Like I say, if you want to go over code from PA5 or any other code, come on in with a laptop and we can work through stuff. Or if you've got any other lingering questions on any of the material, we can talk about that. Otherwise, I will see you either in 215 or for your final exam. All right, thank you.
Yeah.
So, I think, so I mean,